Welcome guys. Now we have the second part. Suppose that f of t, x of t is Lipschitz with Lipschitz constant L, and f of t 0 is 0. Show that f of t, x of t less than or equal to L absolute of x of t. So this is simple. So first of all, what you do is we quote the Lipschitz condition. Okay, so the Lipschitz condition, for Lipschitz condition we have Lipschitz condition we have f of t, x of t minus f of t, x, so we can say x1 of t, x1 of t, okay, should be less than or equal to the Lipschitz constant absolute of the difference of the two functions. So we have x of t minus x sub 1 of t. Okay, but the condition is given to us as f of t 0, okay, should be equal to 0. Okay, so we let x subscript, okay, x subscript t be equals to 0, and we do the substitution. So that means we'll be having f of t, x of t, okay, minus f of t 0 less than or equals to L x of t minus 0. Okay, so when you simplify this, you'll be having f of t, x of t less than or equal to L x of t. Okay, so absolute. So that is it. So that means that L, you have therefore the Lipschitz constant L is f of t, x of t. So that is for the first part. All right, for the second part, you are supposed to show that Gronwall's inequality satisfy this result here using the result in the A, the first one we got, okay, which is this. I have already copied that, and the result in the Lipschitz condition, and also the Lipschitz condition that we've had. So first, what you do is to apply the Lipschitz condition first. Do the substitution. We know from the Lipschitz that our Lipschitz constant equals L absolute of x of t to be equals to the absolute of f t of x of t. Which is the same thing as this here. Okay, so we do the substitution. So we put this in place of this. So we have x of t equals e exponent negative kt x naught plus e negative kt ks. So L absolute of x of s ds. Okay, so the next thing we do is we make all the functions inside the integral the subject. So we already know that we have x of t, which is this, equivalent to this. So we multiply through by this, e exponent k s l. Okay, so we're having e exponent kt l x of t equals, when you use the e exponent kt, this becomes 1. Okay, so we're having x naught plus the same thing here as well, the integral of o t from 0 to t. So we have e exponent ks l x of s ds. Then all these should be multiplied by the l. Okay, so we've used all the two. Okay, all right, so now we divide through by what is in the bracket here, or what's in the brackets here. So we maintain this out. Okay, the reason why we do not add this is because there's already l here, so that when we integrate we can easily do away with this. Okay, so this and this will cancel out. So we'll be having e exponent kt l x of absolute of x of t, okay, all divided by x naught plus e exponent k s l x of s ds, okay, from 0 to t, then equals l. Okay, so with that we can now integrate. So when you integrate with the interval 0 to t, the same thing here to 0 to t ds. Okay, so ds, so this will change to s because of the t here. Okay, so you can do the changing. So we're having, since this and this are the same, so this will go out, leaving the ln of the denominator. So we're having the ln of x naught plus the integral e exponent k s l x of s ds, so 0 to t okay, so a close, and all should be on the interval of 0 to t equals, okay, we maintain this because from the question we are supposed to have something like this. Okay, so I can maintain that. So we having how we can solve it. So we have a, let's solve it. So we have l, let's maintain it. So you have l okay, we solve it, lt, so we have lt, okay, ls ls on the interval of 0 to t. Okay, 0 to t. So this applying the limit, will be having the limit of x naught plus this here will have all this, so the same thing, e exponent ks l x of s ds on the interval this, okay, minus ln of x naught. Okay, when we put 0, everything here becomes 0 and leaving this the constant, so equals lt then minus 0. Okay, so we apply the logarithm rule, so we have the division, so we have the ln of x naught plus the integral e ks l x of s ds all on x naught equals lt. So we simplify this, so this becomes an exponential, so we have x of t plus the integral 0 to t here, so e ks, same thing, ds 0 to t, so equals exponential function with this constants. Okay, so we have x naught e exponent lt. Okay, so with this here, it's the same as our previous equation here. This equation here, okay, is the same as what we've had down here. Okay, what we had down here, when you make when we factorize this out, we factor this out, it comes to this side. Okay, so we have e exponent kt x of t, so leaving this and this and the integral function. Okay, so we'll have all this will be equals to e exponent kt x of t equals x naught e exponent lt. Okay, yeah, so we can move on now. So we have this, let's move on. So we make x of t the subject, so we having x of t equals x naught e exponent lt then times e exponent negative kt. Okay, bringing like terms together, we'll be having x of t equals x naught e exponent lt minus kt. Okay, but note that from our previous solution, okay, e of kt, e exponent kt is the integration factor, so it's the same thing. E exponent kt is the same thing as this, so that means that our this here, okay, so that means but e exponent negative kt will be equals to e exponent negative integral of 0 to 2 kt. k of t dt. Okay, so since we have to use the limit to make it the same as this here, so we'll have 0 to t. Okay, 0 to t. So we can now fix it into this. Okay, so that will be x of t equals x naught e exponent lt minus the integral. Okay, k, so we use ks, so ks ds 0 to t, and this is absolute, this should be absolute, and this is an inequality. So we have that as satisfied, and voila. Don't forget to like, share, comment, and let me know if you have any more questions.